morning, welcome to
KidMath number 79.
KidMath number 79. Okay, today is our second to last movie in our series about square roots and cube roots. And this one's more of a history. The thing we've been talking about is cube roots, and it started with the cube root of 343 equaling 7, and then you asked why was there only 1. Then we learned that the cube root of 1 did have 3 solutions, 1 and then negative 1 plus or minus I times the square root of 3 all over 2. And so the cube root of 343 does actually have 3 solutions. If I just multiply these by 7, we would find 7 and negative 7 plus or minus 7I times 7 times the square root of 3.
I don't think Khan Academy does that one.
Probably not, actually. Probably not. Well, they might. I don't know. But it gets to the point that cube roots have 3 solutions. Square roots have 2 solutions, plus and minuses. Cube roots have 3. Fourth roots have 4. And there's a general theorem called the fundamental theorem of algebra that was first stated by D'Alembert, a French mathematician, in 1746. And it was proved by Gauss in 1799, so quite a long time ago, more than 200 years ago, when he was 21. Now, Gauss had previously done some great work when he was younger. For example, he
summed up 100 in his head. He summed up 1 to 100 in his head.
Yeah, he added up a bunch of integers in his head, but moving on from that, he proved the fundamental theorem of algebra. And the fundamental theorem of algebra states an equation like this. I'll call it x to the n, leading coefficient of 1. Plus a n minus 1 x to the n minus 1 plus a n minus 2 x to the n minus 2 plus blah 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 plus a sub n some constant equals 0. And we've looked at equations like this, like x squared minus 3x plus 2 equals 0, or x cubed minus 1 equals 0. These are just examples. Okay? This equation has n roots. Okay, so this equation has 3 roots, this equation has 2 roots. They may be complex. They might not be real numbers necessarily, like our equation x squared plus 1 equals 0. When we graph this, it's above the axis. It doesn't look like it has roots, but it does have complex roots. In this case, I, plus or minus I.
Yep.
So this equation has n roots. And it's a very important theorem. In fact, it's called the fundamental theorem of algebra. And I'm not going to prove it for you, but I'm going to show you what he did. Okay, so he did it in 2 steps. The first step, step 1, was prove it has 1 solution. There is a solution. And this is kind of cool. So he doesn't start out trying to show that there's n of them. He just tries to show that there's 1. And the way he proved that was by assuming there were no solutions.
Proof by contradiction.
Yeah, so he did it by assuming there were no solutions. And if there were no solutions, there had to be a minimum value of it. I'm kind of rounding corners a little bit here.
Yeah.
There had to be some sort of minimum value, but then he showed that there could never be a minimum value. So that was interesting. That wasn't 0. Okay. So that was that. And then he proved something really important beyond that, that if there is a solution, if, let's call it, C is a solution, then this equals x minus c times x to the n minus 1 plus. So if c is a solution, you can factor out an x minus c from this. And then you can get a polynomial with 1 less degree. So we do this all the time, right?
Yes.
So for example, for the equation I wrote on the board, x squared minus 3x plus 2, this equals x minus 2 times x minus 1. So we could see that 2 was a solution here, 4 minus 6 plus 2. That means we can factor out x minus 2. So you should always think Gauss when you do that. Because x minus 1 is much easier than this. You factor out an x minus 2 and you're left with a smaller polynomial.
Cool.
So once you were left with a smaller polynomial, this you could go back to step 1, then this had a root, then you could factor it out and get a smaller polynomial.
And keep getting smaller and smaller and smaller.
Until you got x to the 0 left, which meant
1.
1. So it took n steps to get there. Pretty cool, right?
Yeah.
That's the fundamental theorem of algebra. Gauss proved this, and it's why we can factor polynomials.
Cool.
And why polynomials of degree n have n roots. Good job. So tomorrow we're going to talk about another mathematician named Galois.